For our next problem, let E be the region inside of the downward pointing cone making an angle of pi over 3 with the negative z-axis, and be inside of the surface x squared plus y squared plus z squared equals 4. And we're evaluating the triple integral of zx dv over E. I'll give you a second here to pause and try to evaluate this region. So my picture for this region is sort of an inverted ice cream cone. So here's the cone, and it's making this angle of if this is the negative z-axis going down, so here's z going up, x, y. This angle here is pi over 3, which means another way to express this cone is that this is the cone, and so I'm going to kind of truncate the cone here. This is the cone phi equals 2 pi over 3, because 3 pi over 3 would be pi, and that's the maximum amount allowable phi. That's the phi pointing exactly along the negative z-axis. So that's the complement of this angle. What we also have is this sphere. And so you can imagine the sphere kind of coming over here and doing something a little bit like this, and kind of exaggerating it. I don't like how I did any of that, so let's graph here first. Yeah, something like this. And so the sphere is, has all sorts of stuff going on up here. But what we're interested in is actually just this little bit here that's putting a cap on this cone. And so the cone, you can imagine you've got the sphere fixed in space. It's a sphere of radius 2. Also known as rho equals 2 in spherical coordinates. And this cone is going to eventually run into the sphere. And when it does, we're kind of flipping to care about the sphere. And the region we're looking at is this bounded zone inside of this kind of sad-looking ice cream cone. It's sad because it's both upside down, and to be honest, it doesn't look very full. I would be disappointed if I went to Jenny's and this was the ice cream cone I got. So, yeah, so that looks sort of accurate for the picture. Now, one of the reasons this region we haven't really integrated things over this before is because in Cartesian coordinates this is totally terrible to try to express. Spheres and cones all have complicated quadratic expressions. You might have to solve for z, and that'll take square roots, negative square roots. It's just not fun. And then the integrals themselves often involve, unfortunately, trig sub. And again, we're trying to avoid trig sub. So how do we do this one? Well, this region is already totally great in terms of spherical coordinates, because in spherical coordinates we're allowing in the xy plane, if you want to pass through this, do you? I mean, in some sense, we're allowing all of the possible thetas, right? Because we could pick any angle theta. Let's go here. So this is my angle theta. You can imagine that coming in here and slicing kind of a piece of this cone. And as you vary theta, you're going to get different slices all the way around. So what we say is because this is rotationally symmetric around the z-axis, theta is going to go from 0 to 2 pi. And that's going to happen a lot in these types of problems. And then we can say, okay, so if you're at any theta you want, you now just want to describe all of the remaining points. And so I'm just going to draw one of these cross sections kind of out floating on its own. And so if we're in r theta, or our rz axis, then what we care about is this, here's negative, here's phi equals 2 pi over 3. So here's my pi over 3 angle. And if I go down, I go 1, 2. Here's my sphere of radius 2. So rho equals 2. And we're trying to express just this region right here. And so I think it should be straightforward that the phi's that we start at are, writing the wrong, phi equals 2 pi over 3, and we keep moving up until we reach our maximal phi, which is here at phi equals pi. And at any given phi in between, we're integrating along that radial slice, which starts at rho equals 0 and goes out to rho equals 2. So my setup for my integral is integral phi goes from 0 to 2 pi. Phi, theta goes from 0 to 2 pi. Phi goes from 2 pi over 3 to pi. Rho goes from 0 to 2. And then I'm left with my two remaining terms. Z, that's rho cosine of phi. X, okay, that's r cosine theta. So r is rho sine phi. And then x is r cosine theta. And now I also need to remember my dv term, and that's going to be a rho squared sine phi d rho. Let me zoom a little bit. Don't love how I did this. D rho, d psi, or phi, d theta. Okay, looks good. So if we zoom and give ourselves a little bit of space to work on this, what we'll have is, let's rewrite this whole integral. We've got an integral with, again, constant bounds, which makes things really nice for us. So 5 from 2 pi over 3 to pi, and rho from 0 to 2. It looks to me like I've got rho to the 4th. I've got sine squared and cosine squared. So sine squared phi, and a cosine phi. Don't combine them. And a cosine theta. And d rho, d phi, d theta. Okay, so let's do each of these on its own. Just eyeballing it, it doesn't look terrible. I've got these rows. So let's give ourselves a little bit more space. So rho is going to give me rho to the 5th over 5, being evaluated from 0 to 2. And that'll give me some constant, which will then multiply by the rest of the integral. And so the next part of the integral to do is the d phi stuff. So sine squared phi cosine phi, I think I should take u to be sine phi. So du is cosine phi d phi. And then this is just u squared. So when I integrate and sub back in, because I just am not going to change my bounds, what I get is u cubed, so sine cubed phi over 3 for that whole section, evaluated from phi equals 2 pi over 3 to pi. And for my last guy, cosine theta d theta, that just integrates to give me a minus, just a sine theta. Sine theta, evaluate from 0 to 2 pi. Which already makes me get 0, because if I plug 2 pi or 0 into sine, I get 0. So this whole thing, when I evaluate, it's going to give me 0. Good job.